Hello everybody, my name is Annika Gomell. I'm a speleoclimatologist from Ruhr University Bochum in Germany, and I spent the last 4 years studying the microclimatology of barometric caves in the US. Today I'm really excited to share with you some interesting findings from my research on air pressure waves inside Wind Cave and Jewel Cave and their significance for the climate inside the caves. As most of you will know, Wind Cave and Jewel Cave are two major barometric caves in South Dakota. They are located in the southern Black Hills and the entrances are roughly 50 kilometers or 30 miles apart. Before I get to my own research, I would like to first give a short general introduction to barometric caves. So, what makes a cave a barometric cave? A barometric cave is defined as a cave in which air pressure gradients between the outside atmosphere and the cave induce compensating air currents. So every time the air pressure on the surface is higher, outside air will flow into the cave until the pressure difference is equalized. If now surface air pressure drops, maybe due to a thunderstorm, air pressure inside the cave will be higher than outside. The pressure gradient is now reversed, and therefore the compensating airflow will change its direction and now flow outwards. If a cave is rather small, or if the cave openings are too large, the internal and external air pressure will always equalize instantaneously, so no pressure gradient can build up and no steady airflow can develop. That means that barometric caves must always have a large volume and a small opening. Let's have a look at Wind Cave and Jewel Cave. Both caves are in the top 10 of the longest caves in the world, so we can definitely assume large volumes. And both Wind Cave and Jewel Cave also have rather small entrances, which make almost perfect conditions for large and lasting barometric pressure gradients between the outside air and the air inside the caves. In my research project, I now wanted to explore how these pressure gradients, which are so important for the whole climate system of barometric caves, can develop. Therefore, I conducted simultaneous air pressure measurements on the surface and at several locations inside Wind Cave and Jewel Cave to compare surface and cave pressure signals. I wanted to know how the pressure signals inside the caves differ from the surface pressure signals, and to understand the related climatological processes taking place inside the caves. Inside Wind Cave, I measured air pressure at 4 locations, including pearly gates, crossroads, elevator, and lakes. As you can see on the cave map, pearly gates, here shown in green, is the location that is located closest to the natural entrance, which is here, then followed by crossroads in violet and elevator in yellow. Lakes in blue, right down here, is located very deep inside the cave. Inside Jewel Cave, I measured cave air pressure at 2 locations. The first one is Spooky Hollow, here, which is fairly close to the historic entrance of the cave, and the other one is Deep Camp, as the name suggests, very deep inside the cave. These 2 figures now show 2 examples of how the air pressure signals look like. On the left, here, you can see air pressure data from Wind Cave. The dark gray line shows the pressure signal on the surface, and then the red, the blue, and the green lines show the pressure inside the cave. And on the right, I have some data from Jewel Cave, where again, the surface pressure signal is displayed in dark gray, and the cave signal is displayed in red. As you can see, the general courses of air pressure look quite similar inside and outside the cave, which makes sense as the atmospheric air pressure waves are transmitted into the cave through the openings. However, they are similar, but obviously they are not the same. So there are also some systematic differences between the internal and external signals, which then cause the pressure gradients, which are characteristic for barometric caves. So now in the following, I would like to present these 4 differences and to discuss how pressure waves are changed as they travel through Wind Cave. So let's start with the most obvious difference. In all measurement series, air pressure inside the cave is always higher than simultaneous air pressure outside the cave, where the absolute difference seems to be approximately constant for each location. The higher air pressure measured inside the caves is simply caused by the lower altitude of the cave locations compared to the surface. So the absolute difference between the internal and external signal is not related to any cave-specific process and therefore doesn't provide any relevant or interesting information on how pressure waves behave inside caves and how they travel through wind cave and jewel cave. The second difference between the cave and the surface signals, which we could find in all measurement series, is a temporal delay. The cave signal, again shown in red, always lags the surface signal shown in gray. In other words, both the highs and the lows of the pressure signals are reached later inside the cave than at the surface. You can see this pretty well in the two figures, where the green lines indicate the positions of the extreme values. For each location, the gap between the lines, and therefore the delay, seems to be approximately constant. What does this delay tell us about pressure waves in barometric caves? It shows that pressure waves cannot easily travel through wind cave and jewel cave, but are slowed down by the small openings and by narrow passages inside the caves. The duration of the delay corresponds to the travel time of the pressure wave from the surface all the way down to the investigated location. We then use cross-correlation analysis to quantify the delay and therefore the travel times for each measurement site. The lag is defined as the value of the shift for which the similarity between the cave and surface signal is greatest, and therefore the cross-correlation is highest. On the left, you can see that the maximum values of cross-correlation, and therefore the delays of the pressure wave inside wind cave, are all pretty close together. As you would expect, they are increasing with increasing distance to the opening and range from 2 hours and 2 minutes for pearly gates to 2 hours and 21 minutes for lakes. In Jewel Cave, the differences of the delays between the investigated locations are much larger. You can see this on the right figure. The delays here range from 38 minutes for Spooky Hollow to 10 hours and 26 minutes for Deep Camp. In addition to the absolute difference between the signals and the delay, the comparison of cave and surface air pressure also revealed a smoothing effect inside Wind Cave and Jewel Cave. Here you can see that many small pressure fluctuations which are present in the gray surface pressure signal cannot be found in the red cave signal. You can see them here inside the green circles. However, the large atmospheric pressure systems, for example, rising air pressure here or falling air pressure here, are transmitted into the cave and can therefore also be seen in the cave signal. These larger pressure systems are so-called cyclones and anticyclones, which last few to several days and move over the Black Hills in a westerly direction. Those much smaller variations, with a much higher frequency and a much lower amplitude on the other hand, are called microbaromes and are related to atmospheric background noise resulting from small-scale weather phenomena. When pressure waves travel through Wind and Jewel Cave, those small variations are not transmitted due to frictional losses at the rugged rock surfaces. Especially in cave areas with narrow gaps and small fissures, the smoothing effect can be quite strong. After this qualitative visual analysis, we also wanted to describe the smoothing effect quantitatively. So I determined the number of relative extreme values as a measure for the smoothness of the pressure signal, where a high number indicates a rough signal and a low number indicates a smooth signal. The bar graph on the left shows the results in absolute values, which also depend on the duration of the measurement series. On the right, the proportions are displayed. Bars in blue show data from Wind Cave, and bars in red show data from Jewel Cave. Bars of the same shade belong to a simultaneous measurement series. As you can see, this analysis also supports the impression we visually gained before. For each simultaneous measurement series of external and internal air pressure, the number of relative extreme values inside the cave is always lower than outside the cave during the same period of time, which indicates the smoothing effect I described before. The fourth and already the last systematic difference between internal and external pressure we could find is the damping of the pressure signal inside the cave. So both the extreme highs and the extreme lows of the surface pressure are attenuated, which causes a smaller pressure range inside the cave. This effect becomes particularly clear if the absolute difference caused by altitude differences is removed from the data. This can be achieved by converting measured absolute air pressure in relative air pressure. For this, the mean of each measurement series is subtracted from all its individual values, as you can see on the right. So here's the formula. So this process then shifts the mean of each measurement series to 0, while all measures of dispersion, such as the range or the standard deviation, are not affected. The right figure also shows that the extreme highs and the extreme lows, so it goes in both directions, of surface air pressure are never reached inside the cave. In simple words, inside Wind Cave and Jewel Cave, the highs are lower and the lows are higher. The main reason for this is that extreme values of air pressure correspond with high pressure gradients and therefore with high airflow velocities. These high airflow velocities lead to an increased share of turbulence, which then weakens the overall airflow and therefore the propagation of pressure waves. Therefore, not the whole range of air pressure is transmitted into the cave and the signal is damped. This effect is also well visible in the corresponding boxplot diagrams. For all locations inside both caves, the range of measurement data is smaller than on the respective surfaces. Again, blue box plots summarize data from Wind Cave, and red box plots show data from Jewel Cave. Before I move to the last part of my talk and explore how these changes and processes are distributed inside Wind Cave and Jewel Cave, I would like to quickly recap what our analyses have revealed so far. Based on our measurements, we could find 4 systematic differences between the air pressure on the surface and inside Wind Cave and Jewel Cave. Firstly, air pressure inside the caves is always higher than at the surfaces due to altitude differences. Secondly, air pressure inside the caves is delayed and lacks the surface pressure due to the small openings and narrow passages which restrict airflow and slow down the pressure waves. Thirdly, air pressure inside the cave is smoothed due to frictional losses at the rugged cave walls. And finally, air pressure inside the caves is damped due to higher shares of turbulence at higher airflow velocities, which increase air resistance. In the last part of my talk, I would now like to do a spatial comparison throughout Wind Cave to investigate how these differences change inside the cave. Therefore, I first need to introduce quantitative measures to describe each process. For the absolute difference, this is very simple. It can be described as the difference between the mean of the cave signal and the mean of the surface signal. As said before, the delay can be calculated by cross-correlation analysis. To quantify the smoothing, the ratio between the number of relative extreme values inside the cave and at the surface is calculated. And lastly, the ratio of the range inside the cave and at the surface is used as the measure for the degree of damping. For each location inside Wind Cave, I selected the longest measurement series with a resolution of 20 seconds to get the best possible results for the spatial analysis. I will now show how each difference changes as the pressure wave travels down the cave. Remember, pearly gates, here on the very left, is the location which is closest to the entrance, and lakes is the location which is very deep inside the cave. The black dots indicate the mean difference between the cave and the surface signal, which ranges from approximately 6 hectopascal at pearly gates to about 16 hectopascal at lakes. So as expected, the mean difference increases as we go down deeper into the cave. The same trend can be observed for the delay, which is shown here in red dots, and which is also increasing towards the deepest parts of the cave. What's very different, though, is that the differences between the locations are actually very small. If we consider how much further the pressure wave has to travel to get to lakes, very deep down in the cave compared to pearly gates or crossroads, it's really surprising that the differences of the travel times is less than 20 minutes. So what does this tell us about pressure propagation through Wind Cave? This shows that the small opening and the narrow entrance area are the strongest obstacles slowing down the wave. And as soon as the pressure wave could pass this part of the cave, then the dense three-dimensional maze structure of wind cave really provides good conditions for a fast propagation of the pressure wave. If we now look at the smoothing factor and how this changes throughout the cave, here it's shown as the green dots, there's the next surprise. There is actually no increase in the degree of smoothing with increasing distance from the cave opening at all, which shows that the whole smoothing process occurs at the entrance or at the uppermost part of the cave. Something very similar can be observed for the damping factor, which is shown as the blue dots here. For every location, the damping factor is positive, which shows that the cave signal is actually damped compared to the surface, but we cannot see an increase of damping as we go deeper to the cave. This suggests that local characteristics related to the morphology of wind cave are more important for the damping than the distance to the opening or the depth inside the cave. And this now leads me to my conclusions. So this study is the first attempt to describe how pressure waves behave inside barometric caves and which processes and mechanisms are related to their behavior. We found that surprisingly in wind cave, the depth inside the cave does not affect the strength of the speleoclimatological processes as strongly as we expected. So instead, the small opening and the narrow entrance area are the most decisive factors for the changes of the pressure waves. In Jewel Cave, this is very different, and most changes of the air pressure signal occur deep inside the cave. Unfortunately, I do not have time to go into more detail here. But what we can say for sure, that it is only because of these speleoclimatological processes we identified and described in this study that pressure gradients between the cave and the surface can develop, and the compensating currents, which are characteristic for barometric caves, are induced. These currents are fundamentally important for the whole climate system of the caves, as they control all elements of speleoclimatology, including air temperature, humidity, and CO2 dynamics. Therefore, this study can be seen as the groundwork for an improved understanding of numerous aspects of the climate systems inside barometric caves. Of course, I don't want to end my talk without saying a huge thank you to all people and organizations who supported us and made this research project possible. This study was financially supported by the Ruhr University Research School, Germany's Excellent Initiative, and the German Academic Scholarship Foundation. We also thank all Wind Cave National Park and Jewel Cave National Monument staff, especially Mark Ohms and Dan Austin. During COVID-19 and the travel restrictions, their support of our fieldwork was more important than ever. And finally, I'd like to thank all of you for taking the time and listening. I'm really looking forward to your questions and an interesting discussion.